All right, we're going to do the second part of our factoring special cases. The last special case that we're going to see in this class is a sum or difference of cubes. All right, so unlike the difference of squares, this one can be a plus or a minus between the two. But the rule is that if you have two perfect cubes, so a to the third and b to the third, whether there's a plus or a minus, it's going to factor as a binomial times a trinomial. Both cases, binomial times a trinomial, right? So 2 terms times 3 terms. In your binomial, your first factor, it's going to be the cube root of each factor. And then in your trinomial, it's going to be the square of the first, the square of the last, and the product of the two in the middle. All right, and then as for the signs, whether it's a plus or a minus, it does follow the same pattern. But as for the signs, this one is going to be the same, right? The first sign that you see is going to be the same sign as what we originally started with. So if it's a plus, it's going to be the same. If it was a minus like it is here, it's going to be the same sign. All right, the second sign that you're going to see is going to be the opposite of what you see in the middle, right? So this one's a minus because this one was a plus. And then this one's a plus because this one's a minus, right? And then the last sign that you're going to see is going to be always plus. Always a plus. Right, so right in front of your b squared, this one's always plus. All right. I would remember that using SOAP. All right, so there's a thing down here, right? SOAP stands for same, opposite, always plus. So even before you start factoring a problem, if you recognize that it's a sum or a difference of cubes, you could set up your binomial times your trinomial, and it can be the same, opposite, always plus, right? Or the same, opposite, always plus, right? So it can set that up, and then you're just filling in the blanks. All right, so let's try that with the next page. All right, so maybe the hardest part of these problems is recognizing that it is a sum or difference of cubes. So looking at something like number 13, x to the third, anything with an exponent of 3, or anything with the multiple of 3 as an exponent, is a perfect cube. Right, so x to the third, if I take the cube root of that, that's just x. Right, but you also should recognize, right, there's a couple main ones that are going to keep showing up. Right, you also should recognize that 125 is a perfect cube. Right, if I take the cube root of 125, it's 5. All right, and you can even verify, right? If I did 5 times 5 times 5, that should get you 125, and you can do the work if you need to. All right, but this is 2 perfect cubes, and there is a minus in between them, so it's going to be the same sign, so x minus 5, opposite, always plus, right? So I have a bi times a tri, so it's going to be x minus 5, and then in your trinomial is going to be the square of the first, square of the last, so 5 squared is 25, and then the product of the two in the middle, 5 times x is 5x. All right, and there's nothing more we can do to that. All right, that trinomial on the inside is never going to factor, right? So you don't really want to do anything with that, right? Some people might see the x squared and the 25 and think that they can factor it as a perfect square trinomial, right? Can't do anything to that. We just leave it alone. All right, so again, the hardest part of this is memorizing the formula and knowing what the perfect cubes are, right? So let's try the same thing with number 14. All right, so number 14, I have y to the third plus 8. Y to the third is a perfect cube. It does have an exponent of 3. And 8 is also a perfect cube, right? That's the same as 2 times 2 times 2, right? Should get you 8. So I can cube root the first, cube root the second. I don't care that the sign is a plus in the middle. This one can be a sum or a difference. So it's going to be same in the binomial, and in the trinomial, opposite, always plus. All right, so same, opposite, always plus. In your binomial, it's the cube root of the first plus the cube root of the second, so y plus 2. And then in your trinomial, it's the square of the first, square of the last, and the product of the two in the middle. So y squared minus 2y plus 4. And then that's all you have to do to that. All right. Let's try the same thing with number 15. All right. It's a pattern. The more you do it, the easier it is to recognize. All right. X to the third, that x1 to 3 is a cube root. Is a perfect cube. And then 27 is a perfect cube as well, right? 3 times 3 times 3 gets you 27. All right. So cube root of the first, cube root of the second. You can fill in your binomial and your trinomial if you'd like. Right, there's a minus in between, so it's going to be the same sign, the opposite sign, and always plus. All right, so cube root of the first is x, cube root of the second is 3, and then in your trinomial, it's going to be the square of the first, square of the last, 3 squared is 9, and then the product of the 2 in the middle, 3 times x is 3x. All right, that's all we got to do to that one. Same exact thing over here. Again, the hardest part is maybe just recognizing that it's a perfect cube. 64 is a perfect cube, right? That's going to be 4 times 4 times 4. 4 times 4 is 16, and then 16 times 4 gets you 64. And then this x has an exponent of 3, so it is a perfect cube. 1 is a perfect cube. It's also a perfect fourth, fifth, sixth, right? So you can go all the way down. 1, no matter how many times you multiply by itself, is going to get you 1. So this is also a perfect cube. There is a plus in between, so I'm going to fill in the signs. It's going to be the same sign, opposite sign, always plus. All right, so then in the binomial, it's going to be the cube root of the first, cube root of the second, cube root of 64x to the third is 4x, and then the cube root of 1 is 1. And then in your trinomial, it's the square of the first. If I did 4x times 4x, that's 16x squared. Square of the last. So 1 times 1 is 1, and then the product of the 2 in the middle, 4x times 1 is 4x. All right, and that's all we got to do to that one. All right, let's do some more examples. All right, so the number 17, we can try the exact same thing, right? 64x to the third, we just did that, right? That is a perfect cube. That's going to get me 4x. And then 27, we also just did that. That is a perfect cube. Cube root of that is going to get me 3. There's a minus in the middle, so it's going to be a 4x minus 3. So same sign. All right, so that was the same sign, opposite sign, always plus. And then we can fill in our trinomial using the cube roots. All right, so 4x squared is going to get me 16x squared. All right, 4x times 4x. All right, so square the first, square the last. So 3 squared is 9. And then the product of the 2 in the middle. So 4x times 3 is 12x. And that's all we got to do there. Super easy. All right. As you know the pattern, it gets way easier. All right. So something like number 18, same thing. We already established that 125 is a perfect cube. All right. Y to the third, anything with an exponent of 3 is a perfect cube. 1 is also a perfect cube. There is a plus in the middle, so let's set up our signs. It's going to be the same, opposite, always plus. All right. So let's fill in the blanks. Cube root of the first is 5y. Cube root of the last is 1. And then in our trinomial, it's going to be square of the first. So 5y times 5y is 25y squared. Square of the last, 1 times 1 is 1. And the product of the 2 in the middle, 5y times 1 is 5y. All you got to do. All right. Now this one, this is not a perfect cube, right? Away. Right, so 3 and 192 are not perfect cubes. Maybe you didn't know that 192 wasn't a perfect cube, but you can tell that 3 isn't, right? There's not a number that when you multiply by itself 3 times, you get 3. So what we can check first is check for the GCF, right? So our GCF, if there is a 3 in front of my 3x to the third, let's check if that's the GCF. All right, so maybe you don't know off the top of your head, but you can use that 3 on the outside as like a clue, right? So I'm going to see if it does get me something that can be factored out. So I can take out the 3, and 3 goes into 19 6 times. All right, do your long division. Bring down the 2, and then goes into 12 4 times, and it goes in evenly. So 192 divided by 3 would get you 64. It does work, right? So I could take out the GCF of 3. And then I'm left with x to the third minus 64. And then notice on the inside, this is a difference of cubes. I have a perfect cube minus a perfect cube. All right, so I'm going to set up my parentheses using the same opposite always plus. So same opposite always plus. And then the cube root of the first is going to get me an x. The cube root of the last is going to get me 4. And then in my trinomial, it's going to be the square of the first. So x times x is x squared. Square of the last, 4 times 4 is 16. And the product of the 2 in the middle, which is going to get me 4x. And then don't forget about the 3 that we factored out on the outside. And so this would get you your final answer. All right, so sometimes there is a GCF. If there is, you just take it out and then factor the inside however you can. All right. Now number 20, this one doesn't have a GCF between 8 and 27. All right, so we would just factor it as normal. 8 and 27 are both perfect cubes, and these both have exponents of 3. So this is just going to get us a regular sum of cubes. All right, there's a plus in between, so I'm going to do the same opposite, always plus. And then I'm going to cube root the first. So cube root of 8x to the third is going to get you 2x. Cube root the last, that's going to get me a 3y in my binomial, right? And then in the trinomial, it's going to be the square of the first. So 2x times 2x is 4x squared. Square of the last, 3y times 3y is 9y squared. And the product of the 2 in the middle, 2x times 3y is going to get you 6xy. And that's all we got to do. All right, so hopefully the cubes aren't too bad. It's quite repetitive once you know the pattern and once you can recognize what the perfect cubes are. A lot of times that's the hardest part, is getting the pattern down and figuring out which numbers are perfect cubes. All right, but once you do it, you can see we didn't show a lot of work for these, right? Because once you know the formula, it shouldn't be too bad to fill in the blanks.